Well, good evening, everybody, and welcome back to another Our Universe Revealed. For those of you who haven't met me, I'm Jonathan Kratt, and I am the series coordinator for this public lecture series from the Department of Physics at the University of Notre Dame. For those of you who've joined us previously, either in person or with our recent set of talks online in the past couple of weeks, it's very nice to have you back with us this evening, and if this is your first time joining us, it's great to have you with us as well. As always, if you want to know more about our series, you can do that via our website, that is nduniverse.org. You can also sign up to our mailing list there if you want to be kept up to date with what we're doing, and you can also find us on Facebook if you search for us there under ND Universe. As has been the case for the past couple of weeks, the format this evening is going to be like we have done, where we'll have a talk, and throughout that we will collect questions as we go. If you're on Zoom, you can use the Q&A feature at the bottom of your Zoom screen there, and you can also use a Google form to do that. I will share the link for that very shortly with you in Zoom, and if you're on YouTube, you can use the chat feature on the right-hand side, or again, I will share that link with you once we get started of the question form you can use to submit any questions. And we'll collate those and then go through them all at the end of the talk. This evening, it's my pleasure to welcome back Dr. Dan Wilkins from Stanford University to Our Universe Revealed. Dan gave us a fantastic talk on campus at Notre Dame back in February, all about his research onto black holes and how they power some of the brightest objects in the universe. Tonight, he's going to talk about another astronomical topic, just sort of where we all come from and what we're made of, what the universe is made up of, and where it all comes from. Dan got his PhD from the Institute of Astronomy at the University of Cambridge in 2013, before he moved to St. Mary's University in Halifax, Nova Scotia. He was a National Fellow of the Canadian Institute of Theoretical Astrophysics, or CETA, when he was there. In 2016, he was awarded the NASA Einstein Fellowship and took that up at the Kavli Institute for Particle and Astrophysics and Cosmology at Stanford University. And today he's still at Stanford with the position of a Kavli Fellow. So welcome, Dan. Thanks for offering to give us a talk this evening. And fingers crossed we can get all your screen sharing and things working.
Okay, thank you, Jonathan, and good evening, everyone. It's a great pleasure to be able to join you this evening and tell you a little bit about how astronomy can teach us about how we fit into the universe, how it all got here, and in a sense, how we're all born of the stars. Gazing into the night sky and across our cosmic neighborhood, we're able to see how the planet Earth fits into the universe. We are one of 8 planets in our solar system, in orbit around our nearest star, the Sun. And our Sun is one of more than 100 billion stars in our galaxy, the Milky Way. By measuring the positions of all the stars we see around us, we can piece together the shape of the galaxy, a spiral similar to M51, the Whirlpool galaxy pictured here. And the Sun is located on one of the outer turns of the spiral of the Milky Way. Our galaxy is one of what is likely to be hundreds of billions of galaxies in the universe. Many galaxies are found grouped together in clusters. This is the Virgo cluster, our nearest such grouping with more than 1,300 galaxies that are all held together by the force of gravity. Beyond the nearby galaxies, we can stare deep into space between the stars and the galaxies that we previously knew about. Combining more than 50 days worth of observations that were taken over 10 years with the Hubble Space Telescope of a small patch of sky, smaller than the head of a pin that's held at arm's length, the Hubble Extreme Deep Field image was produced. By staring for a long time, the Hubble Space Telescope was able to gather the faint light from galaxies extremely far away, and there are galaxies as far as the eye can see. Light travels fast, but it doesn't travel instantly. These galaxies are so far away from us that it took 13 billion years for the light to get here. This light was more than 1/3 of its way here before the planet Earth was even formed. That means we're seeing these galaxies not as they are now, but as they were 13 billion years ago. These are some of the first galaxies that formed in our universe, and by comparing them to the nearby galaxies, we can turn the clock back and learn about how galaxies formed and developed over time. And the galaxies form part of a larger structure called the cosmic web. When we study how the galaxies are distributed through our universe, both in real life, looking at observations of the galaxies, and in computer simulations, such as in the Millennium simulation, the output of which is pictured here, we find that the galaxies are grouped together along strands or filaments of material, almost like the strands of a spider's web. And when the strands meet in this cosmic web, that's where those largest clusters of galaxies, like the Virgo cluster, form. So let's try to work out the recipe for making a universe. How did this cosmic web structure form, and how did the planets, the stars, and the galaxies grow within it? Well, first of all, we need to ask, what is the universe made of? Zooming all the way into the material around us, it is made of atoms. Atoms contain of particles called protons and neutrons that are clumped together in the center in what's called the nucleus. And then there are electrons in orbit traveling around that nucleus. The number of electrons determines the chemical properties of that element, and the number of electrons is determined by the number of protons in the nucleus, with the simple rule that one proton attracts one electron. The hydrogen atom is the simplest chemical element. It just has one single proton at the center with one single electron around it. And on top of all that material, we need a force to hold the universe together. The force that binds our universe together on the largest scales is gravity. Quite simply, gravity is the mutual attraction between every bit of stuff in the universe to every other bit of stuff. Any two bits of material in our universe are attracted towards one another. But this force is so pathetically weak that we don't notice it every day. We don't see ourselves being attracted by gravity to the objects around us. The strength of gravity depends on how much mass there is. The only thing near us with a lot of mass is the planet Earth. So the only thing that we feel a substantial force of gravity from is the Earth attracting us towards itself. But the more stuff you have, the more mass you have, the stronger the gravity attracting things towards it. And this is going to be important later on. A small pocket of our universe that's just a little bit denser than its surroundings, that just has a little bit more in it than its surroundings, will attract things towards it. This means that what begin as small clumps in our universe will grow bigger and bigger as gravity attracts things towards them. Just like the force of gravity holds us down to the planet Earth, the force of gravity from the sun keeps the planets in orbit around it. And the mutual attraction between all of the stars keeps a galaxy together. This image is of the Andromeda galaxy. We can see the beautiful spiral structure. The lights in those spirals are made up of hundreds of billions of stars. They're being held together by gravity, and that gravity is keeping them in orbit, traveling around the center. Even though we might not perceive it here on Earth, our solar system is in orbit around the center of our Milky Way galaxy. The universe is always in motion, and it is always changing. The European Space Agency's Gaia satellite has accurately measured the positions of the stars in the sky. And by accurately measuring not only where the stars are, but how fast they're moving, imperceptible to the human eye, we can predict where those stars will move to as time goes on. ESA put together this movie that predicts what our night sky will look like. This is the band of the Milky Way galaxy as we would see it if we could unravel the sky onto a flat plane. We can predict where those stars will appear to be in hundreds of thousands of years' time, based on how we see them moving. In particular, look at the constellation of Orion, which if you're careful, you can just see on the far right-hand side of the image, just below the band of the Milky Way in the center. See how as the stars move, the constellations that we know gradually fly apart. A pioneer of studying the motion of stars in galaxies was Vera Rubin. She was the first woman allowed to observe at the Mount Palomar Observatory. And when she started her career, astronomy was considered a man's field. Her research in her early career had largely not been accepted by her colleagues, so she chose to avoid the more competitive or contentious research areas. So she began studying the rotation of the galaxies. In the late 1960s and early 70s, she was at the Carnegie Institution in Washington, working with a new sensitive instrument that could measure the velocity of stars at the edges of galaxies. Her first results were announced in 1975, which revealed one of the most profound discoveries about how the universe is put together. If we construct a very simple toy model of a galaxy, Newton's laws tell us how strong the gravity that holds the stars together should be. We can see how many stars there are in a galaxy, and we can work out how strong the gravity holding the stars in on the edge of that galaxy should be to stop them flying off into space. In that simple model, we predict that a galaxy should rotate like the one on the left. The middle should go round fast where the gravity is the strongest, but on the edges, the star should rotate more slowly. This is not what Vera Rubin observed. She discovered that the stars on the outer edge of a galaxy rotate faster than those in the middle. But from our understanding of gravity, and assuming that the gravity comes from the stars that we can see, the gravity is not strong enough to hold those stars in on the edge of that galaxy and stop them flying off into space. This means that we need extra stuff in that galaxy that we can't see. Extra matter that doesn't emit any light, doesn't produce any observable signatures, but it provides gravity. This is what astronomers refer to as dark matter. And I'll let you in on a little secret. Dark is a code word us astronomers use for something that we don't understand. The gravity that holds the stars in a galaxy should also be pulling everything in the universe together. All of the galaxies should be pulled towards one another. But it turns out that our universe is getting bigger. The galaxies are flying away from each other. This was first discovered by Vesto Slipher in 1917, who discovered galaxies moving away from us at around 600 kilometers a second. Then in 1922, Carl Wilhelm Wirtz discovered that the closer galaxies are moving away more slowly than the more distant galaxies that are moving faster. It was Edwin Hubble who understood the importance of this motion and published what we now know as Hubble's law in 1929. Galaxies move away from us, and the speed at which the galaxy moves depends on how far it is away. The further the distance, the faster that galaxy is moving. Most of the original velocity measurements from Hubble's work, published in 1929, came from Vesto Slipher. But by 1935, he had measured more than 150 galaxies using the 100-inch Hooker telescope at Mount Wilson. Actually, in 1927, Lemaitre had shown that Hubble's law, 1929, could be explained by a universe that is expanding uniformly. Every part of this universe is moving apart from every other part of the universe at the same rate. Now, this was really big news. Gravity should be pulling everything together. Newton had realized this. In private letters written to his peers, he had expressed some concern that his ideas of gravity should be destroying the universe, should be crunching everything in the universe together. But he didn't take the ideas much further. Albert Einstein had similar misgivings with gravity. He found the idea of a universe being pulled together so distasteful that he actually fudged the original versions of his equations. He added a number called the cosmological constant that counteracts gravity on long distances to stop the galaxies being pulled together. But following Hubble's work and the realization that the universe really is expanding and that there's no reason to believe the universe has to be static at all, Einstein described adding this cosmological constant as his greatest blunder. If we think about this expanding universe, in which everything is moving away from everything else, and then we think about turning the clock backwards, instead of everything moving away from everything else as time goes forwards, everything moves closer and closer together. We expect everything to have been closer together in the past. Now, light takes time to get to us from the furthest reaches of the universe. The further away we're looking, the further back in time we're seeing, just because of how long it takes that light to have got here from us. So when we look at the most distant galaxies, we're seeing them not as they are today, but we're seeing them long ago, where the universe was smaller and more densely packed. Though it turns out that our universe hasn't simply expanded at a constant rate, as if everything was just simply flying away from a single point at a constant speed. The expansion of our universe is accelerating. The Hubble Space Telescope was named after Edwin Hubble, and not by coincidence. Even though Hubble is a large multi-purpose observatory that's demonstrated its capabilities to do a whole variety of science, when it was launched, it had one key project in mind, and that was to look for supernova explosions, dying stars that blow up in the furthest galaxies. By measuring these explosions in distant galaxies, Hubble was able to work out how far away these galaxies are and how quickly they're expanding away from us to extremely high precision. This led to the amazing discovery that the universe is not just expanding, it is accelerating. An expanding universe could have a simple beginning, everything just flying out at a constant speed from a single point. But for the universe to be expanding at an accelerating rate, we need a force that's pushing things apart. We need a force acting in opposition to gravity. Gravity is trying to pull everything in the universe back together, but there's a mysterious force pushing the universe apart and causing it to expand at an accelerating rate. And you can guess what us astronomers call that force. We use the word dark because we have no idea what it is. We call it dark energy. And by looking at how fast those distant galaxies are moving away from us, we can put together the composition of our universe. It turns out that only around 5% of our universe is made up of the normal matter, of the atoms that you and I and the planet Earth and the stars are made of. Some 25% of our universe is made up of that mysterious dark matter. We have no idea what it is, but we need it to provide the gravity to stop the stars flying away from the outer edges of galaxies. And some 70% of our universe is made up of this mysterious dark energy, the force that's pushing the universe apart and causing the expansion to speed up. Now, in the beginning, the universe was extremely small if we trace it back to when everything was piled up together. And this moment is what we call the Big Bang. Everything, all of the matter and energy in the universe was compressed into a very small volume of space. The whole universe weighs about 10,000 billion tons. Now, if this much material was made of atoms, it wouldn't have fitted into the early universe. So the early universe couldn't have been made of atoms as we know them. It's governed by the laws of quantum mechanics. It's very hot, and it's described by quantum fields that are fluctuating around, just like waves on the surface of the ocean. And remarkably, our laws of physics let us understand this early state of the universe right up to 10 million billionth of a second after the beginning. Going much before this time, everything becomes so small and so dense that our laws of physics can no longer be used to comprehend it. We can measure how fast the universe is expanding, and by tracing it backwards, we can work out the age of the universe. And we can find that the Big Bang happened 13.82 billion years ago. At the start, the universe needed to expand very rapidly, a period we call inflation. And as the universe expands, the energy within it becomes less compressed. So the universe cools. Just after the Big Bang, the universe is small enough, dense enough, and hot enough for 7 minutes that nuclear fusion reactions can take place. At extreme temperatures and pressures, protons and neutrons are forced together, and this starts to form the first small atoms. And then those small atoms are forced together to create larger atoms. In these 7 minutes, carbon, nitrogen, and oxygen were created. But how do we know that the universe expanded out of a Big Bang after all? What if the universe wasn't expanding? Well, the scientific establishment in the 1930s and 40s didn't like this idea of a Big Bang. There was a slight anti-religious sentiment at that time within the scientific community, and the idea of a creation of the universe implied a creator. So an alternative was put forward by Hoyle, Bondi, and Gold in 1948, the steady state universe. Now, they still had to explain the observation that the galaxies are moving away from us. So they came up with a picture in which the universe was unchanging, but it was dynamic. Imagine it like a river. The river itself is constant, but the water flowing through the river is always moving. They came up with this theory in which the galaxies move apart, but as the galaxies move apart, more matter is created in the gaps to fill in the space. And this was something they called the C field. Now, this may sound completely ridiculous. If galaxies were just coming out of nothing as the universe expanded, surely we'd be able to see this stuff appearing. Well, it turns out you only need one particle per cubic meter to appear every 300,000 years. So actually, maybe it's not such an obscure idea. So what we really need is an experiment or an observation we can go and make to prove or disprove the beginning of the universe in a Big Bang. Well, our story now turns to Arno Penzias and Robert Wilson working at the AT&T Bell Labs in 1965. They were working with a horn antenna that had originally been used to test communication with the ECHO satellite, one of the first experiments communicating with satellites in orbit around the Earth. After the ECHO experiment, this antenna was going to be used for radio astronomy, for looking for radio waves coming from deep in space. and Penzias and Wilson were tasked with calibrating the noise in this antenna. They found, somewhat frustratingly, that wherever they pointed this antenna in the sky, they got the same noise being picked up in their electronics. They were convinced something was wrong. They tried everything to get rid of this noise. They even climbed inside the massive antenna and cleaned out what they euphemistically referred to as the white dielectric material that had been left behind by birds nesting inside it. But this signal was still there. These radio waves coming from all throughout space. Robert Dickey's group at Princeton were preparing the same type of experiment and found similar things. In discussion with Penzias and Wilson, it became apparent they had discovered what we refer to as today the cosmic microwave background. The cosmic microwave background is a natural prediction of this theory of a universe that begins in a Big Bang. By the end of the 1960s, physicists really had to embrace this idea of a beginning to the universe and of there being an early universe. So how does this microwave radiation permeating all of space show that there was a Big Bang? What are these microwaves? What are we looking at? Well, in the beginning, the universe was small and dense. Everything was too hot for the electrons to stay trapped in orbit within atoms. So instead of having atoms with protons and electrons, we had the nuclei, and then we had the electrons moving around freely. When electrons are free, they absorb and they scatter any light that tries to travel past them. So in the beginning, the universe was opaque. Light could not pass across the universe. But as the universe expanded and cooled down, the electrons joined back onto the atoms, so now they were out the way, and that light in the early universe could freely propagate to reach us today. But the universe is expanding. As the universe expands and cools, that light gets stretched out, so that high energy light becomes the microwaves that we see today. They've become stretched out so much that these microwaves have the equivalent temperature of minus 271 degrees Celsius. And we are seeing a snapshot of that moment just after the Big Bang, when the universe became cool enough that the electrons rejoined the atoms and that light could at last travel freely. In 1989, NASA launched the COBE satellite that carefully measured the temperature of this cosmic microwave background over the whole sky. They found perfect agreement with the predictions of the Big Bang theory to less than 0.03%. And the fact that this temperature is so consistent over the entire sky means that the beginning of the universe had to be small enough that this temperature could be communicated everywhere. In 2001, COBE was superseded by WMAP, which was able to measure the cosmic microwave background at higher resolution, starting to resolve structures in it. And then in 2009, Planck produced the highest resolution map we have of the cosmic microwave background of the whole sky. This is that snapshot of the universe at the moment light was able to travel freely. And each little hotspot that you see in this image is a little clump in the early universe. That early universe was like the wavy ocean, everything moving around, but those waves start to freeze out as the universe expands, leaving some patches of the universe that are slightly more dense than others. But these little bits of the universe that were left more dense have a stronger gravitational force attracting material towards them. So these little clumps that start off just a tiny bit denser than their surroundings grow and grow and grow and become a lot denser. These tiny little specks in this image are the seeds that grew the galaxies that we see today. So adding that to our schematic, we have the Big Bang, followed by our 7 minutes of nuclear fusion to create the first chemical elements. And then the cosmic microwave background is that snapshot of the universe as it expanded out from the original Big Bang. Each of those little clumps attracts the material around it. What starts off as a small clump gets bigger and bigger and bigger, growing the seeds that eventually grow into the galaxies and the stars that we see today. But then the universe went dark. The original universe was hot, so the material in it was still able to glow. But as it expands, it cools down, and we start to lose the sources of light that we had early on. That is until we're able to light up the first stars. Gravity keeps pulling the clouds of gas together within the galaxy, and eventually that gas gets squeezed together so much that the pressure gets so intense at the center of the cloud that that nuclear fusion process is able to be triggered again. This nuclear fusion process that creates the first starlight. The first starlight doesn't appear till something like 150 million or even a billion years after the Big Bang. But this star formation process has produced some of the most spectacular images of nebulae that we see in the universe. This is the Eagle Nebula in the constellation of Serpens. Zooming in on this cloud in the center, the Hubble Space Telescope produced one of its most famous images, the Pillars of Creation. These are giant plumes of cosmic gas being pulled together by the force of gravity, being pulled together into stars. The column on the left is 6 to 7 light years long. It's so big that light takes 6 to 7 years to travel from one end to the other. And the tiny little finger that you can just see sticking out of the top is the size of our whole solar system. All of that gas and the dust that surrounds it blocks the visible light. But if instead we look at infrared light that can pass through the dust and gas, we can see those new stars lighting up inside the cloud. This image was taken with NASA's Spitzer Space Telescope. So how do we form the planets around the stars? Well, it's exactly the same process that formed the stars. It's gravity. So that new star has formed in the center, and it was left with a disk of leftover gas. Some bits of that disk happen to be slightly more dense than their surroundings, so the gravity starts to attract clumps together in the disk. We form rocky clumps in a protoplanetary disk shown in this artist's impression. And those clumps travel in orbit around the star, gradually accumulating more material and growing into the planets that we know about. We're able to see this process in Fomalhaut B. This is an image taken with the Hubble Space Telescope of a brand new star in the center that's been blocked out in this image. And that scattered light all around it comes from that debris disk, of that leftover material. And if we zoom in where that small box is, we can see a little clump that traveled round between 2004 and 2006. This is a brand new planet growing in the disk around a young star. So we can put together our history of the universe, all the way from the Big Bang, 7 minutes of nuclear fusion, that moment we see in the cosmic microwave background that gave us that first convincing proof of the Big Bang. We can then understand how gravity pulled material together, growing the galaxies, the universe going dark before the first stars lit up, and then the galaxies that we know about today, the galaxies that we can see, growing throughout the history of the universe with new stars forming within them and planets forming around those stars. But unfortunately, the universe I've just described is pretty boring. This universe only has hydrogen, helium, a little bit of carbon, nitrogen, and oxygen, but nothing like the amazing variety of chemicals that we see around us and that make us and that make our habitat. So we need somewhere in our universe with the high densities, temperatures, and pressures that are required for nuclear fusion to join those light elements together that we made just after the Big Bang into heavier ones. We need the stars. Stars are the giant nuclear reactors that produce the chemical elements. Throughout most of their life, a star is just crushing together hydrogen atoms and forming helium atoms. This is the process that powers the sunlight coming from our own nearest star. But our sun isn't hot enough to squeeze helium together into anything bigger. We need to wait until a star comes to the end of its life. When a star runs out of the hydrogen it needs to keep its starlight running, it loses the thermal pressure holding it up. So gravity pulls it together, crushing down that star. But as the gravity crushes down the star, that crushing force starts to heat up the gas again, and it squeezes together the helium atoms that were left over. This causes the outer parts of the star to expand into a red giant. Now, when our sun expands, it will go from 430,000 miles in radius to 90 million miles in radius, probably coming out very close to where we are. And this leaves a red giant star. In the center of that red giant, the crushing force from the gravity is the greatest, so the temperatures and the pressures are highest in the center, and it gets cooler and less dense on the way out. So our red giant ends up with a layered structure, producing all different chemical elements throughout its structure. On the outer edge, where it's the coolest, we just have hydrogen turning into helium. But then further in, the crushing force gets greater, the temperature gets higher, so helium is crushed into carbon and oxygen, carbon turns into neon and magnesium, and all the way down at the center, things like oxygen get turned into silicon, and silicon can be turned into nickel and iron. But unfortunately, we can't make anything heavier than iron. It's just not possible to squeeze nuclei together inside a star. So then the star runs out of fuel. It's not able to carry on this nuclear fusion once it runs out of things to squeeze together. When the most massive stars run out of fuel, stars more than about 10 times the mass of our sun, they explode in spectacular supernova explosions. This supernova explosion is critical to scatter those elements we've made throughout the universe so that we can use them. And then what's left at the center keeps on collapsing. Gravity keeps crushing it together. And something that's about the mass of our sun, 2,000 billion kilograms, is compressed to be smaller than the combined size of South Bend and Mishawaka. This is about 10 times denser than the nucleus of an atom. The electrons and protons get squeezed together. They turn into neutrons. And if the star isn't too heavy, these neutrons can resist the collapse being forced upon them by the gravity, leaving behind a neutron star. Now, many of these neutron stars are found in binary pairs, which slowly spiral in towards one another. They eventually collide. Now, if two balls, each about as heavy as the sun and compressed to the size of a small city, collide at half the speed of light, it produces extreme conditions, forging the heavier elements like gold and platinum. So astronomy can start to point us towards the answers to some of the most profound questions. We can see how our planet and our solar system fit into the galaxy. We can work out that the majority of the universe is made out of mysterious dark energy and dark matter. We can observe parts of the universe so distant that we see them not as they are today, but we see their history, a snapshot of how they were when the light left on its long journey to get to us. And we can measure how the universe is expanding and turn the clock backwards towards the Big Bang. The diverse array of chemical elements that make up the planet Earth and that make us are produced by nuclear reactions that happen throughout the life cycles of stars. And this tells us that our sun and our solar system, because they contain so much iron, because they contain gold and platinum, they must be at least the second generation of material, having already been recycled through the life and death of an earlier star and thrown out in a supernova. So in conclusion, we're all made of stardust. Or perhaps we're just nuclear waste.
Excellent. Thank you, Dan. Thank you for working through those technical issues we had. And for those of you on YouTube that the feed dropped out, I see many of you came across to Zoom. So thank you very much for making that journey. We will figure out what happened with that and make sure it doesn't happen again. As a reminder, if you want to submit any questions in Zoom, you can use the Q&A button at the bottom. I've also just sent the link out to our Google form. We've already had a few questions, but if you do have any burning questions you want me to put to Dan, put them in through either way, and we'll do it now. So we've had a few questions already, Dan. The first question was about, right back at the start, that Hubble Ultra Deep Field image you showed. What do those galaxies look like now?
So that's both a difficult and an easy question to answer. The easy cop-out way of answering that question is we have no way of knowing what those galaxies look like now. They're so far away from us that the light has taken 13 billion years to get here. That means to see what they're like today, it's going to take 13 billion years for that light to get to us. But actually longer, because the universe is expanding and they're moving away from us. So we have to wait more than 13 billion years to see what those galaxies look like today. But we can actually compare those galaxies that we see early on in the universe with the galaxies that we see close to us today. And we can see all the galaxies in between. And this teaches us how galaxies have evolved over time. We can see what an early galaxy looks like. In that Hubble Extreme Deep Field image, they were sort of weird, irregular shapes. They hadn't quite grown into their mature forms. But as we go to the galaxies of today, we can understand that those immature galaxies will have turned into more ordered structures, like the beautiful spiral of the Andromeda Galaxy or the Whirlpool Galaxy. And then sometimes those galaxies will collide with other galaxies that leaves these big blobs, these giant elliptical galaxies.
Okay, good. So they kind of, we don't really know, but they're going to look different from how we saw them then. So nice. And we had another question that came in, and it was about when we're sort of looking at things from the past from one year to the next, do things change much in that period of time, kind of in a one Earth year?
So the overall structure of the universe doesn't change much. I showed that animation, the predictions of how the stars in our Milky Way galaxy will move. And in those predictions, for us to actually perceive the stars moving to different positions on the sky, and for us to see the constellations lose their shapes and to take on new shapes, will take hundreds of thousands of years. But things do change much more quickly. One thing that we've really been discovering over the last probably even 20 years, if not less, is that our universe is truly dynamic. While the backdrop of the stars and the galaxies might look the same, we see these fantastic explosions going off. We see supernova explosions that appear one day out of almost nowhere, and then they fade away over the months and years to come. We see black holes swallowing the material around them, letting off these enormous flashes of light that last only days. And this is something that we're really just starting to scratch the surface of. We're seeing things change more and more rapidly, but with the next generation of telescopes, particularly the Vera Rubin Observatory that's being built in Chile at the moment, that's going to be scanning the whole sky and surveying the whole universe night after night, we're going to see these rapid changes and explosions happening all through the universe and much more.
Excellent. We've got two more questions for you, and then we'll wrap up. So there was a question of, will the sun create kind of all of those heavy elements that you were talking about there at the end?
So the sun will produce the elements probably up to around iron, the things that we can make by normal nuclear fusion in a red giant star. So the sun at the moment is just turning hydrogen to helium. When it runs out of hydrogen, probably in about 5 billion years, it'll expand into a red giant, and that red giant will start cooking up carbon, nitrogen, oxygen, neon, silicon, all the way up to iron, which is less than halfway up the periodic table. But after our sun runs out of fuel in its red giant phase, it doesn't really have enough energy within it, energy that's provided by the gravitational force crushing everything together, to really go much further than iron. And it'll just shrink down into what's called a white dwarf, which will gradually cool down and fade away. In order to make those heavy elements, you need the really big stars. You need a supernova explosion, and you need to leave behind a neutron star that can collide with another neutron star to make the heaviest elements.
Awesome. I think you've answered one of the questions we just had, which came in, which was, can gold be made by a supernova, or is it only made by colliding neutron stars? So that answer says it's only by colliding neutron stars and big things together. So we've already answered that one before it came in.
Almost. So actually, if you read an astronomy textbook that was probably contains theories from 10, 20, 30, 40 years ago, then that will tell you that gold is made in a supernova explosion. And one of the big discoveries of nuclear astrophysics that actually professors at the University of Notre Dame have played quite a big role in, it turns out actually a supernova explosion, it's quite difficult to make gold in. It's quite difficult to make gold actually form in a supernova explosion. So you really do need something more energetic like these colliding neutron stars to produce the right conditions. But that's something we've only known about for the last few years.
Okay, great. Two final questions. So there's a couple of good ones come in. We'll start with the easy one, which is, are there multiple universes?
Oh, if that's the easy one, I dread to hear the hard one. So the answer to that really depends on what you mean by a universe. And there's different ways we can consider multiple universes. So our universe is expanding. And in the beginning, our universe expanded extremely rapidly. That means there are some parts of our universe that are more than 13.82 billion light years away. Now, light would take 13.82 billion years to get to us from 13.82 billion light years away. The universe is only, in inverted commas, 13.82 billion years old. So any bits of our universe that are more than 13.82 billion light years away, we have no way of knowing about. The light from them hasn't had time to get to us yet. Now, as the universe gets older, more light will have more time to get to us. So gradually bits of the universe will come into view. Unless bits of our universe are expanding so quickly that the expansion means that before the light has time to get to us, it's expanded even further away. So you could mean a multiple universe, just parts of our universe that we have no access to. We can't travel there, we can't receive any light from it, we can't learn anything about it. There could also be multiple universes in the sense of things that we consider fundamental physical constants, like how strong gravity is. the force holding an atom together, things like that, things that we consider fundamental constants of nature, but have values that we just have to go out and measure. There's no reason they couldn't have different values in different parts of a very big universe. So gravity could be stronger or weaker in another part of the universe. So while the laws of physics are fundamentally the same, the actual way they play off each other could be slightly different. And then there could be the true meaning of other universes. Whereas our universe that expanded out of that Big Bang contains space and time all wrapped up together. So all the space and all the time that we conceive is part of our universe. But you could have another universe that started from another Big Bang somewhere else, outside in the multiverse, the collection of all the universes. We have no direct way of interacting with those universes, although there are some exotic theories of multi-universe physics, still ideas, nothing really proven, that there are ways that those multiverses, those other universes, could leave imprints in our universe.
Got you. So another one that's kind of a maybe, but we haven't got a way to test it. So good. So the final one, and it's coming back a little bit to your research, so keep it short. Do all galaxies have a black hole at the center?
We believe so, yes. Certainly all the big galaxies should have a black hole at their center. We can see in our own galaxy, there's something holding in the stars very close to the galactic center in orbit. And that something has to be a supermassive black hole. We can see supermassive black holes in other galaxies when they start to swallow the gas that's around them. And these actually light up to power some of the brightest objects that we see across the whole universe.
Excellent. Oh, still going? Well, I just want to thank you again, Dan. Apologies to everyone who's been watching. For some reason, Zoom decided to stop sending the stream out to YouTube earlier on. So we'll figure out what happened with that. Hopefully we have the Zoom recording of this, and we'll try and get that up on YouTube. We also have the talks from the past couple of weeks up there as well. Next week, we're going to be moving a little bit away from astronomy, but to a topic which is physics related, and I think is particularly interesting because it has a humanitarian aspect. I'm delighted that we're going to be welcoming Professor Graham Peasley from the physics department at Notre Dame to join us next week. He's going to be talking about his research studying PFAS, which are per- and polyfluorinated alkyl substances, and their impact on the body and exposure to firefighters, first responders, the environment, and the public. For those of you who are Notre Dame football fans, who watched the games on TV, in the 2019 series, he was featured as part of the What You Would Fight For video. If you're following the chat, you can see that there. I've just posted the link to the YouTube videos. You can go watch the short commercial that was made about his research, and he's going to be joining us the same time next week and talking about his research and the impacts. So very exciting, slightly different topic, but I hope you'll join us then. All I have left to say is thank you very much again, Jan. Thank you all very much for joining us, and stay safe out there, and hopefully see you next week. Bye-bye for now.